Yeah, today we'll go through the carbohydrate module, and we'll cover this module in two separate recording. The first recording will go through the carbohydrate definition, naming, and physical properties. So, and the second one then we'll go through the chiral characteristics of the carbohydrates and the chemical properties, and the last topic in the second recording will go over the applications of the carbohydrates. So, carbohydrates definition. Carbohydrates are really nothing mysterious about them. They are really aldehydes and ketones. So they are aldehyde and ketones, but they are really very, very unique aldehyde and ketones. Why? Because they have many hydroxyl groups, and they do have similar chemical properties and reactions. However, the physical properties might differ a little bit, according to their densities, to their solubilities. Okay, so the carbohydrates are considered a source of energy and transport and storage in insects, bacteria, plants, as well humans as well. Carbohydrates are chemical compounds found in nature, in plants, in animals, and they are produced in animals in a process called glycogenesis through the glycogen breakdown. Glycogen will be introduced later on in the second recording. Carbohydrates contribute to sweet compounds found in nature, such as the kitchen sugar, sucrose, honey, fructose, and glucose, and potatoes, which are really made of polysaccharides, amylose. Now we'll start naming the type of the carbohydrates and naming those carbohydrates. Now, there are three types of carbohydrates. Those carbohydrates, as you can see, they are monosaccharides. So we have, as I said, let me repeat myself again, three types of, and they are monosaccharides, disaccharides, and polysaccharides. And as you will see, that the glucose is really the heart of this carbohydrates naming and build up. So it's really building the whole carbohydrate. So glucose is the most important unit of all these three types: monosaccharides, disaccharides, and polysaccharides as well. So let's go first. We'll go through this step by step here. And if you look here, the first one here, we have galactose. This is galactose here, sorry. This is galactose here. And this is glucose. So you'll ask yourself, what is the difference between them? They look almost similar. Yes, but here we are. If you look at this OH here, the position is this OH, and the position of this OH here. Here it is. Let me circle it. Yes. So you can see there is the difference here. In galactose, at carbon 4, this carbon 4, the OH is up. In the glucose, you see here, this carbon number 4, this carbon number 4, the OH is down. So if the OH is down at carbon 4, we call this one glucose. If the OH is up, we call galactose. So you can see the difference between galactose and glucose. Only the carbon 4 carrying out OH. If the OH is down, that's glucose. If the OH is up, that's galactose. Now let's look at the types of drawing those carbohydrates. Well, here we have, if you look at this, we have, let's count this one here. This is carbonyl group of aldehyde, correct? 1 carbon, 2, 3, 4, 5, and 6. So those are 6 carbons, okay? And this is cyclic. This is cyclic, means non-cyclic, means is normal non-cyclic carbohydrate. This is the same molecule here, correct? This is the same molecule, but is now cyclic, correct? And if you look like this and this are similar. So this is glucose, correct? And this is the same glucose. However, this called here Fischer. Let's put this one here with F, and this called Howard H here. Let me take it out. This this called Howard. I'm trying to get the H here. As you see here, this is H here. So as you can see, this is a Howard, here it is. This is Howard structure, the cyclic, and this is non-cyclic called Fischer structure. Both of them glucose, but both of them drawn or they have different structure. Both of them can be present, but the most stable one is the Howard structure. This is the most stable. Let me just. This is the most stable structure is the cyclic one. The cyclic one is the most stable structure compared with the non-cyclic one. So here we can go and look at the whole thing. So we have here a Fischer. This is, as I said, this is Fischer here. Fischer projection, you can see here it is. This is Fischer, oops, sorry. Yeah, this is Fischer projection. This is Fischer projection, as you can see. And the way we can, through the IOBC naming, we can go and count the number of carbons. First of all, we have to see what this really is. The first, as we said, the carbohydrates are ketones and aldehyde with this special number of hydroxy groups attached to the carbons. We have plenty of hydroxy groups, but here is an aldehyde group, so we name this one aldo. The name is, again, repeat myself, is aldo. Now next I have to come and count the number of electrons. As you see here, 1 in red, 2, 3, 4, 5, 6. That's a hex, so there will be hexo. So will be aldo hexose, and the ending will be OSE. So this one here, as I said, an open, non-stable. As I said, it's open. The Fischer structures are not stable type of structures, but they are present though. They are present, but the cyclic one are more stable. Called Howard projection. So, but again, this naming is IOBC name is called. It's an aldehyde group. Start with the aldehyde group, aldo. How many carbons? 6. Hexo, and then the ending OSE. So this one, hexo. Then we will see later on the last OH here. we have to consider it. This is at the left here, OH. So it will be L. L-aldohexose. L-aldohexose. Now, another one here we have to pay attention for. This is, although both of them are here is Howard structure. And if you look at this, the OH, if the OH in the top here and the OH in the bottom here, correct? So we have to pay attention if the OH is the top or the H at the bottom. So when it's at the bottom is an alpha, when it's up is a beta. So you have just to pay attention for the OH here, at the first carbon. This is the first carbon here. So here it is. Here's the first carbon. Okay, so the first carbon, and here is the first carbon. So the OH is down is alpha, the OH is up is beta. Correct? And this is a Howard structure as the most important. So this is beta glucose and this is alpha glucose. Okay, now let's look at the cyclic ones, but not, if I can go back and look, this is called 6-member ring, correct? 6-member ring. But now we have even very interesting 5-member rings. And this is the common name, as I said, glucose, as we can, let me go back and here. This glucose, beta and alpha and beta glucose, yes, this is a common name. And we said this is the real IUPAC name for this will be, depending on the OH position up and down. This is, for example, here. Let's look at this. Let's look at this again. Let's look at this here and tell me what that really is. This, you'll start here. This is an alpha, correct? And that's IUPAC name. Alpha, and then it is a glucose, will be alpha glucose, correct? Alpha glucose, that's a common name. But how about if you say this is, you know, the structure of the Fischer, you know, non-cyclic. That will be what? Will be, you have to look at the, when it's cyclic, non-cyclic, the OH here will disappear, will be then, you look at the OH, the last OH left or right. So it will be like here in the top, look at the top one here again. The non-cyclic. The OH at the left, correct? That will be L. Aldo, here it is, aldohexose. L-aldohexose. And here the cyclic one will be alpha glucose. That's a common name. Another common name is the OH up will be beta glucose. As you will see later on, it's very easy to name them according to the common names. You will see later on, we'll talk about when it comes to disaccharide and polysaccharide, it's very, very hard to follow IUPAC name because it's become very, very complex to name them according to IUPAC naming, and therefore we use the common names for the carbohydrate. Easy to figure out the name, the common name. Now this is 5-member ring called fructose, correct? You can see it. That's fructose, and this is, again, this is Howard cyclic ring, and most stable, correct? Most stable. You can write the fructose in a Fischer non-cyclic ring, which is here. That's a Fischer one, correct? As you can see, that's a cyclic or Howard, the cyclic or Howard ring, and this is a Fischer, less stable. But again, you can still see the difference between the Howard and the Fischer. Now the unique about this fructose, it has what? It has a keto group. So the function group is not aldehyde, it's a ketone group, correct? That's a ketone. And it will react chemically, and it has physically the ketone physical and chemical properties, correct? So now if you look at this one here, CO here, if you look at the CO here, that's a ketone. And then will be keto. Then you start counting the number of carbon. 1, 2, 3, 4, 5, 6. Correct? So this is a keto, and then you look at the OH here, left or right. This is left. So will be L. So the name of this will be L. Correct? L, because the OH at the last OH is at the left. L, and this is keto. Correct? And 6 hexose. Keto hexose. L keto, because of the keto group, ketone carbonyl group here, keto hexose. So now, the disaccharides types, we have 3 types here. We have disaccharides. As you will see, that the glucose is the building structure of those disaccharides. So we have maltose, we have lactose, and we have sucrose. Three types. And the building structure is, as I said, is our glucose. So now let's go further here. So those are now those maltose, lactose, and sucrose. So you will see maltose is 2 units of glucose connected via alpha 1,4 glycosidic bond. So they are alpha, so they are connected to this alpha 1,4 glycosidic, and you can see it here. This is the bond here. This is the alpha 1,4 glycosidic bond. Correct? That's maltose, 2 units of glucose. Now, lactose and again, it's 1,4, correct? And if you look at this, lactose is a little bit different. Look at this lactose here. Lactose is made of 1 unit of galactose and 1 unit of glucose connected via beta 1,4 glycosidic bond. So this is different a little bit. If you look at this, this is the OH is up, that's galactose, and here was the OH is down in the first, in the number 4. Here's the OH down, that's glucose. Correct? So they are connected, galactose with glucose, the beginning, connected via, this is down like this, correct? Goes down like this. So this is beta 1,4 glycosidic bond, and therefore you will see this is called lactose. So, and here just show you here, show you this is glucose is made of galactose and glucose connected to each other. Now let's go to the third one, sucrose. This is sucrose. It has the same thing here. Sucrose is made of 1 unit of beta D fructose, which is the 5-member rings, if you recall, and 1 unit of alpha D glucose connected via alpha beta 1,2 glycosidic bond. Correct? So one is, this one here is glucose, and this is fructose, correct? And connected through the 1,2 beta 1,2 glycosidic bond. This is, if you look at this bond here, this is glycosidic bond 1,2 bond. So this is, and sucrose is called the sugar cane or table sugar, kitchen sugar. The polysaccharides naming is, the IBC name is, as I said, is very hard, and you can see the polysaccharides example is starch and glycogen and cellulose. We have 3 types. Let's look at the starch. Starch is a form of glucose storage in plants, correct? Starch is made of 2 things, 2 molecules or 2 compounds, 2 carbohydrates. One is called amylopectin and amylose. Amylose and amylopectin. Amylose is about 80%, okay, of content of the starch, and amylose is 20%. Now, ask yourself, what's the difference between those two? Well, it turns out to be amylose is more linearly connected. Those glucose, the connection of the glucose is connected linearly, and the amylopectin is, you have a lot of branching. Every 25 glucose unit, you have a branch, correct, of the of glucose unit. So that's the difference between amylose. Amylose is as it says here, you see 250 to 4,000 alpha D glucose connected linearly. So that is via 1,4 glycosidic bond, and this is very important. Amylopectin, we have the branching now, start not only linearly horizontally, but start building up vertically, connected to layers, like layer 1, layer 2, layer 3, and the connection will be through the 1,6. See, after 25 glucose unit, you have this vertically alpha 1,6 branching glycosidic bond, correct? So that's the difference between amylose and amylopectin. And I think there will be a picture, so I'm not sure. Yes, here it is. So you can see that's very nice, linearly connected, all these units of glucose. Here, the other one, well, we have a branch. Every time, see the branch here, up, branch down, branch up, down, up, down, up, down. So it start branching every 25 units. So very frequent branching. The glycogen, the second part of polysaccharide, we said starch, and we said glycogen, and we said the cellulose. So this is the second, glycogen is the second part, correct? And this is a second part of the polysaccharides, and this is found in the animal. The only difference between glycogen and then is like amylopectin, but it's really like amylopectin. Here, let me just put this one here, show you here. This glycogen looks like this, like the amylopectin. However, the difference between them, the frequent branching is not there. So in amylopectin, we have 25 in the top here. So look at the top, every 25. Here, we have not every 25, we have very less frequent branching. So you have the units is every 10 to 15 glucose, we have a branch. So it's not that much of frequent. And this is glycogen is based on the animal, correct, in the liver. And this one, amylopectin, in the plants. So that's the two differences. The branching, very frequent in amylopectin. Glycogen is no branching. Then amylopectin in plants, glycogen in animals, correct? And cellulose here, the last one here, you'll see cellulose is linear. See how nice, this is glycogen to show you that's the picture of glycogen. And if you look at this, this is the branching here happening every 10 to 15 units of sugar. Not the amylopectin in plants, it has every 25, very frequent. But and this is in plant. In animals, that's the animal here, including humans. This will be glycogen is less frequent branching, every 10 to 15 units sugar, glucose. Now cellulose, the last one. Now if you look at the cellulose, very interesting. Cellulose is really made of glucose, but this time here is linearly connected, but not to alpha 1,4, but through beta. See here, this is very important. Here it is. This is hundreds and hundreds of glucose connected. But what's the connection? The connection is here it is. The connection is via beta 1,4 glycosidic bond, and this is very important, very, very important. It's not like the amylopectin of plants and then the amylose. This one here through alpha 1,6, this is beta 1,4 glycosidic bond, and you can see here This is the connection here. See how nice? See, almost linearly here. See, and they connected to alpha 4 between them. See how nice linearly alpha 4 glycosidic bond here. Okay, so and the question sometimes is asked, why cellulose is digested in animals, not in humans? Well, it turns out the animals they do have microorganism mechanism that's really helping them eating this cellulose, which is really wood, correct, found in wood, and a piece of paper, so whatever, anything cellulose can be eaten by animals, but not humans. They are lacking this enzymes to digest the cellulose, to break it down. So we don't have as humans the enzyme that can break the beta 1,4 glycosidic bond, while the animals, they do really have bacteria and microorganisms initiate for them some enzymes that can in their stomach can digest the beta 1,4. And last thing here for the first recording, I want just to let you know that's what we went through. That's how to name those according to your IBC name. We use the Greek numbering, 1 mono up to maybe 10 deca, octa, 8. So we went through that and we explained everything about this. And here is the name, how to show this is the OH here left, correct? And we go for the OH here is aldo, that's IUPAC name, aldo, and then number of the carbon 1, 2, 3, 4, 5. That's pentose. 5 means pentose. So that's the OH at the left. So aldobentose. So aldobentose, 5 carbons. And here we have 1, 2, 3. And this is carbonyl group. That's aldo. The OH, however, in the right will be D, correct? The IUPAC name will be D-aldotriose. 3 carbons, 1, 2, 3. So this is 2, this is 3. So this is D-aldotriose. So there are some common names, and it's easy to use. That will be glyceraldehyde, glyceraldehyde, D-glyceraldehyde, correct? And here we have the same one. The OH is that in the left will be, the common name will be L-glyceraldehyde or L-aldotriose, IUPAC name. And you can look, and the other ones is the same thing. Here we have a keto group, correct? That will be, and the OH in the right will be D. And the number of carbon 1, 2, 3, 4, 5, 6. So this is ketohexose, correct? That is ketohexose, and D because the OH at the right. And here is the same thing, is this is the carbonyl group is here, and count the number of carbon is 1, 2, 3, 4. That will be D aldotetrose, IUPAC name, and the common name is called D therose. And here is the same thing, but the OH at the left, not here, the OH is at the right. So this is L-therose or L-aldotetrose. So we went through this. This is the same thing, naming. And this is, we went through again how to name those common name and versus IUPAC name. So as I said, naming those carbohydrates, as long as they are monosaccharides, is easy. But when it comes to disaccharide and polysaccharide, it's very hard. We use just the common name, not the IUPAC naming. So here we just put emphasis on how complex IUPAC naming for disaccharides and polysaccharides. the carbohydrate physical properties. The very unique thing about carbohydrates, the monosaccharides, and we'll go to disaccharide, for example, the highly solubility in H2O. If you look at this, galactose, glucose, fructose, those are monosaccharides, are highly soluble in H2O. They have melting point and freezing point very high. You can see they melt at higher temperature, and their densities above H2O, they are more dense than H2O. So they are more dense than H2O, as you can see. The disaccharides, they're really the same thing, correct? They are really the same thing. And the maltose, lactose, sucrose, and all very unique. They are all of them water soluble. Of course, you have many hydroxy groups, correct? And therefore, through the hydrogen bonding, the solubility will be easy, and then the solubility will be high. The higher the hydroxy group, the higher the solubility. So the higher the hydrogen bond formed with H2O, the higher the solubility. So they are really soluble, and their density, even the monosaccharide with disaccharide, the density is almost identical, not the same, but almost, very close to each other. And this freezing and melting point still very high in disaccharide as well. And if you heat monosaccharide and disaccharide and polysaccharide, they tend to decompose at higher temperature. So there is no boiling point for them. So they decompose, and the decomposition products are CO2 and H2O. So it's a sort of combustion is happened to them. And the polysaccharide is the same thing. But the unique thing about polysaccharide, their solubility in H2O will be limited. And you see, because their molar mass is very high, correct? Very high molar mass. And now with the start of the solubility will be restricted, and the hydrogen bond is not that many as in mono and disaccharide. So their solubility limited only, hot water. They are in hot water insoluble, starch, hot water soluble. That's the amylose not soluble in hot H2O. Amylopectin, because it has a lot of units of hydroxy group, so they are hot water soluble. And then glycogen is slightly soluble, correct? And cellulose, of course, they are wood, three woods, and they are not soluble in H2O. Again, at a boiling point, at higher temperature, they tend to decompose. So there is we don't know what's the boiling point of them. They are more dense. The polysaccharide, again, the same thing, than the H2O. More dense than the H2O, correct? All of them are white powder. And the freezing point, again, are very high compared to the mono and disaccharides. Now let's look at the last thing here for this for first recording of the PowerPoint presentation for the carbohydrates. We look at the molar mass. You will see it is very hard for the mono and especially disaccharide. The polysaccharides is a different story. The monosaccharides and disaccharides, you will see the molecular formula is identical. See here, identical. And the molar mass identical. See? Therefore, will not help us to know any information unless we go for the cyclic Howard structure and or, correct, Fischer structure. So to know this, how they are in space. So we have D-galactose and we have D-glucose, D-fructose. Well, but they have the same molecular formula, the same molar mass. We cannot really, from this information, having a lot of benefits unless we have with them the Howard cyclic structure or the Fischer non-cyclic structure. And we can go the last one here. This is the disaccharide, the same thing. You can see they have the same molecular formula and the same molar mass, correct? And then the names is different: maltose, lactose, sucrose. How we know this? We have to do we have to draw their cyclic Howard structure or the non-cyclic Fischer structure to know them. However, now if you look at the polysaccharide, as I mentioned before, this is totally different story. The molar mass is different. Amylose, this is molar mass. Amylopectin is higher in content of glucose, so higher molar mass. Glycogen in animals is a higher molar mass as well. Cellulose is less. This is just the molar mass per glucose unit, so you can see is even higher molar mass for the cellulose. And the molecular formula, you see all the time different, totally different. So polysaccharides differ a little bit in their molecular formula and their molar mass from mono and disaccharide. Thank you very much for your attention, and we'll resume the second section of the carbohydrate